Before we proceed to calibration, let us state the scale after choosing the scale, both for the L-axis and for the R-axis. It says 2 cm represents 0.06 ohm, no longer unit. Remember, when we did not know what X and Y represented, we used the word unit. Now that we know that R stands for resistance, we don't have to say unit, just unit. Instead, we have to state the unit of resistance, and that is ohm. It has this unit. It is either you put this symbol here or you write ohm in full the way I have done here. But by all means, desist from using the word unit when you have known the unit of the parameter or physical quantity you are plotting on a particular axis. We know that on vertical axis we are plotting resistance, so don't use the word unit for it. Instead, use ohm, which is the actual unit for resistance. So 2 cm represents 0.06 ohm on vertical axis. I didn't say ohms because 0.06 is not up to 1, let alone being more than 1. So it remains singular, ohm. The same thing applicable to the second one. 2 cm represents 2 meters on the horizontal axis. 2 cm, that is one interval, represents 2 meters on the horizontal axis. This is summary of these statements. Now let's make progress to calibration. And now step 3, that is calibration. Let us start with calibrating the horizontal axis. This axis, that is the L axis. We should not forget that the scale we got is that 2 cm represents 2 meters. Therefore, from here to here represents 2 meters. That means 2, 4, 6, 8, 10, 12, 14, then 16. Let's see these figures written. Yes, see those figures written against the intervals. Let us go and calibrate the vertical axis in a like manner. In calibrating the vertical axis, we recall that every 2 cm represents 0.06 ohm. That means that from here to here, which is 2 cm, will be equivalent to 0.06 plus the next 0.06 in that manner until the end of the calibration. Let us see these numbers written against the intervals accordingly. All right, there we are. This is the vertical axis being calibrated according to this scale. Scale is approximately equal to 0.06. That means that from here to here, which is one interval, corresponds to 0.06. The next will be gotten by adding this 0.06 to the same 0.06 to give us 0.12 plus another 0.06. That will give us 0.18. Another 0.06 will give us 0.24. In that manner until the top of that axis, that is 0.60. And now step 4, that is locating tabular values on the axis. The time has come for us to locate these values along the L axis and then these values along the vertical axis. Let us start with the formula which you have known before. What is it? Let's see. We recall that the formula for locating tabular values on the axis is N is equal to V over B. B is the value of one unit box. Let us find this B separately for both vertical and horizontal axis. Afterwards, we check how to adapt this formula for both axes. Let us start with the L, the horizontal axis. What is the value of 1 unit box for this L? Let's find out. In effort to find the value of the one small box for each axis, for L, given that the formula for finding one box is given as B is equal to S over N, where S is the scale and N is number of boxes in one interval. By substitution, we recall that the scale for the axis, that is L axis, is 2, and number of boxes in one interval is 10. What it means is that the value of one box along the horizontal axis is equal to 2 over 10. That is scale 2, and then number of boxes in one interval 10. 2 over 10 is equal to 0.2. Therefore, most essentially, let us bear it in mind that as we continue, every small box along the horizontal axis is equal to 0.2. BL means one small box along the L axis, or along the horizontal axis in this case. Likewise, we go to R axis, that is the vertical axis. One small box based on this formula is equal to 0.06 over 10. Don't forget that the scale we found for this R was 0.06. Therefore, scale 0.06, number of boxes in one interval 10. 0.06 over 10 is equal to 0.006. Therefore, BR is equal to 0.006, meaning the value of one small box, one unit box along this axis is this, 0.006. At this point, we take these values back to this formula. For L, we're going to replace this B with this 0.2. For R, we're going to replace this B with 0.06. And they remain constant throughout the time we shall plot these values on the table. Let's make progress. Now, recalling the value of the small box for each of the axes, we conclude that for L axis, that is the horizontal axis, the capital N for it is equal to V over 0.2. I hope you remember how it was done. Then if you do, this one too will be clear to you. For the vertical axis, capital N for it is equal to V over 0.006. These are the formulas for locating these values on their respective axis or corresponding axis. This is a formula for locating these values on L axis. This is a formula for locating these values on R axis. Let us append these formulas near the end or at the end of each axis so that constantly we refer to it as we locate all these values. It might be true, in fact it is true, that on this L axis, all of these numbers are found, marked on the axis, but that does not make this formula invalid. In fact, this formula is more authentic than relying on seeing these values written on the axis, because the next axis will reveal the superiority of this formula over the expectation that each of these values will be found on the axis. Consequently, we mark this at one corner of each axis. For this vertical axis, we have written this result, this one, that n is equal to v over 0.006. From now on, that is until the end of this graph work, this formula will be helping us to determine positions and values. I repeat, throughout the remaining time of this graph work, this formula will be helping us to determine positions and values. The same thing is to be done for the horizontal axis. Let's watch it. Also for this axis, that is the horizontal axis, this is going to serve us for locating positions and values throughout the remaining time of this graph work. It says n is equal to v over 0.2. I repeat, for locating values and determining the values of positions, this is going to serve us throughout the remaining time of this graph work. Let's make progress. Now we paste this table at this point so that we can make easy reference to it as we locate these values on each column that is corresponding to L on this axis. We want to locate these two. It is true that it is here, but we want to make use of this formula so that we don't rely on being able to get the values on the table already marked on the axis. It is frustrating to look up to a number on the table as being marked on the axis already and not finding it. Though all these numbers 2, 4, 6, 8, 10 are marked here, it is not good to rely on such. So let us use this value to make it more authentic. Please, let's do as before. We are looking for this value. What is it located? Place these two where this v is, so that n is equal to 2 over 0.2. What will it be? Let's see. When v is replaced by 2, see it here, over 0.2, the answer is equal to 10. Please confirm. What it means is that to locate these two, we should count 10 unit boxes from the origin along the L axis. Let's count. From here to here is 10. That corresponds to 2. Next is this 4. Let's check. Replace this v with 4 and let's see what it is going to be. Now we see that 4 over 0.2 is equal to 20. It means to locate this 4 along this axis, count 20 unit boxes from the origin. Let's count. From here to here, 10. Next, 20. Therefore, this is the location of 4. Let's locate 6. If we replace this v by 6, we have 6 over 0.2. The answer is equal to 30. Meaning, if you want to know the place where this 6 is located along this axis, count 30 unit boxes from the origin along this axis. Let's count 30. From here to here, 10, another 10, 20, another 10, 30. And surely it corresponds to the place where 6 had been written before. Let us locate 8. Now we see we have replaced this v by 8. We now have 8 over 0.2. And the answer is equal to 40. What does this mean? To locate this 8 along this axis, count 40 unit divisions or boxes from the origin. Let's count 40. from origin along this axis. From here to here, 10, another 10, 20, another 10, 30, another 10, 40. And this corresponds to the place where 8 has been standing before now. Let's now ultimately locate 10 along this axis. Let's see. Now we see V replaced by this 10. We have it that we have 10 over 0.2, and that is equal to 50. Please confirm as before. What it means is that if we must locate this 10 along this axis, we should count 50 unit boxes beginning from this origin. Let's count 50. From here to here, 10, 20, 30, 40, 50. And that corresponds to where 10 had been written before. What a wonderful exercise. An exercise of using a formula to locate each value on the table along the axis. Let's do a similar thing for this vertical axis, the R axis. We recall that this is a formula for locating values on this axis. V is the value we want to locate, and N is number of boxes you must count to locate it. Let us turn our attention to the table again for us to use this formula to locate the values. The R is now what we want to locate. Now let us locate the position for this 0.26 along this axis. That we do by replacing this V by 0.26. See it here. 0.26 over this 0.006. See it here. If this is done, the answer will be equal to 43.3 approximately. What does this mean? It means to locate this 0.26 along this axis, count 43.3 small boxes. You might wonder, what is 0.3? It simply means if you mentally divide one small box into 10, take about 3 divisions and stop there. That is 0.3. After counting 43 full unit boxes, let us now try to get the counting of 43.3 unit boxes along this axis, beginning from the origin. Let's count. Now we begin to count from here. 10, 20, 30, 40, 41, 42, 43. It now remains 0.3. If we want to approximate it, we can as well leave it at 43 and cut off this 0.3. But for more accuracy, we still get that 0.3. Let us now mark the position for this 0.26 after we counted for 3.3 unit boxes. Let's mark it. With a slash, I have marked the position of 0.26. Therefore, this, just a short distance above 0.24, what we get is 0.26. 0.26 corresponds to this point where I marked with a slash. Let us do the next. The next is locating this 0.31 along this axis. We do it by replacing this V by 0.31. See it done here. 0.31 over 0.006 is approximately equal to 51.7. What does this mean? To locate the position of this 0.31 on this axis, we count 51.7 unit boxes. That is roughly 52 boxes. But for accuracy, we insist on 51.7 unit boxes. Let us count this number beginning from the origin. Let's count. To start, we start from here. 10, 20, 30, 40. Remember that at 0.24, we have counted 40 unit boxes. Let's continue to count. The 40th was here. Then 50, 51. We now treat the next box by breaking it into 10 mentally and picking 7. Let me mark the position of 0.31 around this place. Let me mark it. Now this is the position of this 0.31, just a short distance after 0.30. This is convincing, I believe. Let us now go and locate the position of this 0.38. The same thing is to be done. We have it that to locate this 0.38, we replace this V by 8, giving us 0.38 over 0.006, and that is approximately equal to 63.3. 63.3. That means to locate this 0.38, we count 63.3 unit boxes from this origin along the y-axis. That is the vertical axis. Already, we know that when counting, this place corresponds to the 40th unit, 40th box. That means 50, 60. Next is what? 61, 62, 63. The next box will help us get 0.3. Let me mark it as usual. This is the position of this 0.38. Two more values are remaining to be located. They are 0.43 and 0.51. Notice that there is none so far among the values found in the column of R that had been located by coincidence according to the calibration of this vertical axis. Everything had been done with this formula. That is why we must not always wish that after calibration, every value you see on the table must be seen marked on the axis. The formula is more reliable. We now locate 0.43 in like manner. We do it by replacing this V by 0.43 to give us 0.43 over 0.006. When done, we have approximately 71.7. That means to locate this, count this number of boxes. Let's count. To make it easy, we recall that this place, counting from the origin, is already 40 unit boxes. Let's continue. 50, 60, 70, 71. The next box will help us get 0.7. Let me mark it. That is the position of 0.43. Let us now turn our attention to the last value on the R column, that is 0.51. Now we have it that to locate this 0.51, we replace V with 8, so that we have 0.51 over 0.006, and that gives us exactly 85 unit boxes. So like before, let us try to count 85 boxes from the origin and up until we get to 85. So please recall that before we saw that this place corresponds to the 40th box. That means the next is 50, 60, 70, 80, then 81, 82, 83, 84, 85. Let me mark this 85, which tells us the position of this 0.51. Let me mark it. That is 80 here, 81, 82, 83, 84, 85. So this is the mark of the position for this 0.51. We have finished also locating these values on the table along this axis, one of the most crucial stages of plotting graph. Having done the same thing for both axes, we have to move on to the next stage, and that is locating spatial points of intersection. Let's do it. Now, step 5, that is locating spatial points of intersection. Like before, to do it, you go back to your table. This is table we have been trying to plot on this graph page. To start with, we have 2 against 0.26. Let us see where in space 2 will meet 0.26. Let us see. Remember, 2 for L and 0.26 for R. Let's see. 2 for L and 0.26 for R. Let us see where they meet. 2 will go up vertically and 0.26 will come out horizontally. They meet somewhere here. Let us mark the place where they meet, and that is their spatial point of intersection. Let's mark it. This is their spatial point of intersection. Back to the table. 4 for L and 0.31 for R. Let us see where they are going to meet. This is 4 for L. It begins to move up. It is going to meet 0.31 somewhere above. Let's see where it meets it. 4 is still moving up to meet 0.31. Where? Somewhere at this point. Look at this 0.31. Don't forget that we have used slashes to mark the positions of these values on the table here on the axis. So here corresponds to the position of 0.31, which is this. So 4 has climbed up to meet it somewhere here. Let us see how to mark this place where they meet, their spatial point of intersection. This marks the place where both values meet in space. Let's do the same thing for the remaining values. That is 6 against 0.38, 8 against 0.43, 10 against 0.51. Let's see. All right, this is what we get after we got other spatial points of intersection for the remaining pairs of values for L and R. See them. Anyway, at this point, the next is going to be how to run a line of best fit. But bear it in mind that in the past, we did not have a need to develop line of best fit. But take a look at this. Maybe there will be a need to develop that concept of line of best fit. In the meantime, this is the array of points of intersection for the pairs of these values. Now we take on the last stage, the last step of plotting graph, that is running the line of best fit. I stated earlier that in this case, there is need to develop the concept of line of best fit. The line of best fit is a line that will best describe the formula connecting L and R with these points in space. If you watch these points, the way they're arranged, you discover that it is not possible for a straight line to pass through all of them. They are not all on the same straight line. Please watch again. Or are they on the same straight line? By the time you place your meter rule, you discover this fact. Because they cannot all enter through one straight line, but they appear to be roughly along the same straight line, we are convinced that this is a straight line graph. This is not a curve. It is a straight line graph. Despite the fact that all the points may not enter through or into that straight line we intend to draw. Line of best fit is about drawing a line through these points so that that line, when used, can give us a formula connecting the length and resistance accurately as it is in real life. Anyway, how do we develop or run the line of best fit? We do it with three formulas or three methods. What I mean is that there are three methods, three known methods that have been tested to work when we want to draw a line of best fit. These methods are majority method, symmetry method, and least square method. We are not going to be concerned with least square method because it is a bit more advanced than what we are doing right now. So we're going to concentrate on the other two, the majority method and symmetry method. Let me explain what each of them is. Let me start with majority method. What does that mean? It means drawing a straight line that connects majority of these points. A straight line that connects majority of these points. If you're able to get 3 out of these 5 connected by a straight line, then, and the other 2 fall off, that line you have selected is called line of best fit based on the concept of majority. We can also make use of symmetry method. What does that mean? Symmetry method means that if a straight line runs through these points, any one that is not connected by that straight line, all those points that do not fall into that line are not to be found on the same side of that straight line. If this point, for instance, and this point do not enter into that straight line, this and this must not be on the same side of that straight line. And if they fall on opposite sides, their distances from that straight line must be equal or nearly equal. That is what you mean by symmetry method. There is something about this second method. That is that sometimes we can draw a line of best fit in a way that after it is drawn, none of those points enters, or only one may enter, or only 2 may enter, but others which are not entering are symmetrically distributed around that straight line. That is what causes us to name it symmetry method. Which one do you think we're going to make use of in drawing a line of best fit for these 5 points in space? Do you think we must use majority method, or do you think we're going to make use of symmetry method? Anyone that works for us, we're going to make use of it. Let us navigate our way around these 5 points with these 2 methods in mind. That is the line of best fit. You could get something similar to what is already on the screen, as you see, but this is the best I could get. Based on the 2 methods considered, this is the best line to help find the formula connecting the length and resistance. Which one do you think worked here? Let us find out if what I used is majority method. First, how many points entered? We have 1, 2. Only 2 out of the 5 points entered. What it means is that majority of the points did not enter this straight line, which means that it is not that method that worked here. Majority method did not work, which means it falls on the second method. That is the symmetry method. Just watch. Symmetry is not about number. It's about distance from the line of best fit. Watch 3 points that did not enter. This, and this. Each of them has a distance from the line of best fit. And this one falls this side, while these 2 fall off this side. And the distance from this point to the line of best fit and that of this point to the same line are almost equal. And the same thing applicable to this one from this point to line of best fit. So the distances of those points that did not enter to this line of best fit are almost equal. Because of that, we say that this method that worked is symmetry method. It does not mean that at all times, if you want to draw line of best fit, that what you must insist on is that of symmetry method. Many times, what works for people is majority method. But when it comes to symmetry, please make use of it. It is highly acceptable. So far, this is line of best fit for these 5 points. Remember that the reason why all the points did not enter is that this table was obtained not from existing equation, but from experiment. It is a human. It is somebody that was reading the length on meter rule and resistance on multimeter or other devices he used. Humans make mistakes. Because of so many factors, mistakes abound in what humans do, including carrying out experiments. Because these values were obtained through experiment that someone conducted, a human, then mistakes can't be avoided. Because of that, all these points couldn't have entered. Whenever experiment is conducted and all the points enter, then that will be a near perfect experiment and by a perfect human, which is almost impossible in world of today. Let's now move on to the next objective of this work.